Assalamu alaikum wa rahmatullahi wa barakatuh. Bismillah ar-Rahman ar-Rahim. Inshallah, today we will finish the first order logic session. We have just a remaining part that is an application of generalized modus ponens, and then inshallah we'll start the new session. I think we stopped here last time. We defined what we mean by generalized modus ponens and how we can apply it. What is remaining is that we take an example of a knowledge base and apply generalized modus ponens there using forward chaining. I just want to remind you that to apply modus ponens, we will have to have an implication statement like that, okay, which we call it also definite clause, and we need to find the unification of the premises. Okay, so every premise here has to be unified with some facts from the knowledge base. This unification will be done through a substitution. If we can do that, then we can entail the conclusion after we do the substitution. So that's the generalized modus ponens, and there are two conditions to do that for a knowledge base. To use forward chaining with generalized modus ponens is to have all the clauses to be definite. Okay, which means they are all implications like that with positive premises, or simple statements like this one. Okay, the other condition is that all variables have to be universally quantified. So if there is any existentially quantified variable, then we'll have to instantiate it before we apply the generalized modus ponens and forward chaining. So let's go through the example together. Here is a knowledge base expressed in natural language, and we have a query that we want to prove. We want to show how we can entail it from that knowledge base, and we will do that using inshallah forward chaining. To do that, we have to convert, of course, these sentences into knowledge base in first order logic. Okay, so we'll go through the sentences together, and we'll see how we convert them before actually we do the entailment. So the knowledge base says that the law says that it is a crime for an American to sell weapons to hostile nations. The country, called Nuno here, an enemy of America, has some missiles, and all of its missiles were sold to it by Colonel West, who is American. Okay, so these are actually multiple sentences, multiple facts. We want to convert these facts into first order logic. Why? Because we want to prove that Colonel West is a criminal. So that's the query here, and these are the sentences that comprise the knowledge base. Okay, so the first step is to convert every sentence into first order logic. And remember, we need to have definite clauses. So we need to think about, when we do the conversion, we need to think about two things. We need to think about how to convert every sentence into an implication statement, which means if then. So we need to think how we can express this sentence in another sentence that says if something, then something else, or simple predicate as we saw in the previous example. Okay, so let's go through every sentence and see how we can convert it. The first one, it is a crime for an American to sell weapons to hostile nations. So how can we express that? So that of course that's very clear that we cannot just say one predicate. Okay, so it has to be a compound statement, and let's see how we can do it using if then. So it is a crime for an American to sell weapons to hostile nations. So how can we say it? We can say if I am an American, or if someone is an American, and that American sells weapon, which means that also there is something that called weapon, to hostile nations, then this person is a criminal. Okay, so there is a condition here and there is a conclusion. So the condition is we have X is American, Y is a weapon, X sells Y to Z, and Z is a hostile nation. Okay, so that's the condition. If that's the case, then X is criminal. And that's of course universally quantified, because that's like a rule, general rule, right? So if X is an American and Y is a weapon, and X sells Y to Z, and Z is a hostile country, then X is criminal. Okay, so that's conversion from this natural language into a definite clause. Another one, Nono is an enemy of America. That's very simple, right? So we don't need to make it an implication here. It's just a predicate that says that Nono is an enemy of America. Okay. Third one, Nono has some missiles. So actually we are going through the sentences in the knowledge base that we saw in the previous example. Okay, Nono has some missiles. Whenever we say this some word, that means that we should have some, there exist, right? So here there exists a missile that is owned by Nono, right? So there exists missile X, and X is owned by Nono. So that's another predicate that says that Nono owns X. Okay. So that's the conversion of this. Now we have a problem. We said that we have to have definite clauses, and if there is any variable, it has to be universally quantified. That's not universally quantified. That's existentially quantified. So we have to instantiate it. Okay. So we have to instantiate it. We have to replace X with maybe M1, which means Messiah. Okay. So we replace X with M1, so we'll have two now predicates, Messiah M1, which means M1 is a Messiah, and Nono M owns Nono M, which means Nono owns M1. Okay, now we cannot have this with and here, so I cannot put this with and here, because that will make it non-definite clause, right? A clause has to be a disjunction, so that we have to then break it down into two sentences like that. Okay? Remember, in the knowledge base, everything is ANDed. And we have all the facts to be ANDed because we assume that all of them are true. Okay? So that's not a problem when we separate them apart. The next sentence, all of its missiles were sold to it by Colonel West. So this is a bit complicated statement. First, we see all, so we have to. So that means that we have to we need to use universal quantification here. Now, its missiles. So that means that if there is a missile, and its here means it refers to the country, right? Refers to Nono. Okay. So we have to say this missile is owned by Nono, were sold to it by Colonel West. So if there is a missile and that missile is owned by Nono, then remember that we need to see if then, right? So then it is sold by Colonel West. So sold, we have to have a sells again predicate. Okay, so for all X, if X is a missile and X is owned by Nono, that's the condition. Then West, because it's sold by Colonel West, right? So West sells X to Nono. X is the quantified variable here. Okay, so you see this sentence. All of its missiles were sold to it. What is the pronoun here? It refers to Nono. Okay, so sold to it. The last one here is the one that the buyer. Okay, so West sells X to Nono. That's the conclusion. So if X is a missile and owned by Nono, then it is sold by it is is, which is X here, solved by West to normal. Okay? The next one, West, who is American, so that's simple predicate. West is American. Then missiles are weapons. Missiles are weapons. Okay? Now, how can we express this? Missiles are weapons. This is the same like all missiles are weapons, right? So if X is a missile, then X is a weapon. Okay? So for all X, if X is a missile, then X is a weapon. The last one, an enemy of America counts as hostile. So we need also to, so this is a general rule, so it should be universally quantified. So if there is an enemy, if something is an enemy of America, then it is hostile. So for all X, if X is enemy to America, then X is hostile. Okay? Any questions about this conversion? Any questions? Faisal, do you have a question? Your mic is on. Yes. Yeah, sure. Yes, we need to have some time, of course, to think about it. Yes, but do you have any question about these conversions? Are these clear now after I explained them? Faisal? Okay, good. Okay, so now that we converted everything into first order logic and definite clauses, now let's apply forward chaining. So to apply forward chaining, we always start with the known facts. What are the known facts from this knowledge base? What are the known facts? Okay, so this is a known fact. 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 Okay, all of the ones that are not universally quantified are known facts. Okay, or ground facts. Okay, ground facts or simple predicates. Okay, the others are of course also known facts, but they are quantified. Okay, but what we start with in forward chaining is the specific facts that are not quantified. Okay, we call them ground facts. So we start with these 4 facts, and in forward chaining we try to come up with new rules by applying the generalized modus ponens here. In proposition logic, we were applying the resolution rule. Here we will apply the generalized modus ponens. Now, to apply generalized modus ponens, we have to unify the premises. So for every ground fact here, we'll try to unify it with one premise of an implication statement. Okay, so for example, this one can be unified with the condition of this rule. Okay, with the substitution x substituted by x1, x substituted by m1. Okay, so that will entail or will infer the conclusion of this with the substitution that we did, which means we'll substitute x with m1. So we will infer weapon of m1. Okay? Right. Can we also do something similar? We see this sentence, okay, and that can be unified with this one, right? You see here, enemy X America, enemy no America, so that means that with this substitution, these two will be identical. Okay, now this is a premise, which means that by this substitution, if we apply it to the conclusion, we can entail the conclusion with the substitution. So we can entail hostile of what? We substituted x with no. So here we substitute also x with no. So that will be hostile no. Okay, so that's another sentence now to be added to the knowledge base. What else? How about this one? Can we apply generalized modus ponens here? Look at this. Messiah x and ons no x. So we have Messiah m1, so that can be unified with this one. And we have also ons no m1, which can be also unified with this one. Okay, so we will apply generalized modus ponens with these two. Okay, so with this two, we substituted x with m1, so we'll substitute x with m1 here. So that will be cells west m1 no. Okay, type. Can we now apply generalized modus ponens to this one? In order to answer this question, we need to look at the premises and see if we can unify every one of these with something that we know already as a ground fact. If that's the case, then we find out what is the substitution and apply it to the conclusion to get a new fact about the conclusion. Yes, Faisal? Yes, sure. Yes, so which means that we would substitute x with west. Okay. Yes. Yes. Where is that? Oh, yes, this one. Yes. Yes. Yes, so we can do something like this. All of these four can be used to infer criminal of what? So what is x here? X is substituted with west, right? So that will be criminal west, and that's exactly what we want to infer. Thanks, Faisal. Okay, that's exactly what we wanted to entail. Okay, so that's the query. Questions, Abdurrahman? Did you check the homework? Yes. What? Sorry? If I remember correctly, yes, there is. And there are also, if you look at the textbook, there are exercises at the end of each chapter. You will find more exercises about that. Okay, you're welcome. Any questions about this example? Look at the exercises also at the, as I said to Abdurrahman, at the end of each chapter. If you have any questions, let me know in the office hours or email me or talk to you to the TA at any time. Okay, I mean the office hour, or you can have an appointment, of course. Any questions on this? So if you don't have any questions, then of course this is the solution. And this is the forward chaining algorithm. So this is very similar to what we saw already in the propositional logic. We get the input to the algorithm is the knowledge base and the query that we want to entail, or we want to know whether we can entail or not. And basically in this loop, we try to apply the generalized modus ponens. Okay, so the application of generalized modus ponens is this part. So that is the generalized modus ponens. We just here for each rule, we do a process called standardizing the variables, which means that just changing the variables so that they are unique across different rules. Okay, we talked about that in the previous lecture. Okay, so this is just giving different names for variables so that we don't have any problems like what we had in the previous lecture. Then we look at every possible substitution. So this is the loop for a rule. So given a rule in the knowledge base, we try to apply the generalized modus ponens by finding a substitution to its premises. Okay, so here we have these are the premises of the rule. Okay, from here. So we'll have to find a substitution such that this substitution, if it's applied to the premises and applied also to the non-facts, other non-facts in the knowledge base, then we can apply it also to the conclusion. Okay, so that's the unification part that we did in the previous example. Once we do this, then we get the substitution, and then we apply the substitution to the conclusion. Now, if this Q prime, that's the new rule that we should add to the knowledge base, is unified with the query, then we are done. If not, we just add it to the knowledge base and continue. Okay, so this algorithm will end in one of two cases. Either we find it. Either we find the unification, which means that we should return the answer, okay, to the caller of the function, of course, or we don't find any new rule to add to the knowledge base. In this case, we just return false. So if at any case we cannot apply generalized modus ponens anymore to any rule in the knowledge base, then there's nothing we can do, and we'll just stop and declare failure. We just say that false, we cannot entail this sentence from the knowledge base. Any questions about forward chaining? So that's exactly the same like what we did in propositional logic. The only difference is that instead of applying the resolution algorithm to two propositions or two definite clauses, here we apply the generalized modus ponens on the rules that we have in the knowledge base. That's the only difference. Questions? So everything is clear? Okay, so in this case, then we are done with this session, and inshallah now we'll switch to a completely different session, which is probabilistic reasoning. Let me make sure that I share here. Okay, you see now, I think, the new slides? Okay, good. Okay, so this is a completely different session. that has nothing to do with what we studied so far in the course, which means that it's kind of new or a fresh start to you for the remaining part, inshallah, of the semester. So from now till the end of the semester, we will be talking about this session, which is a very important session, very foundational session for AI, which is called probabilistic reasoning. So far in the course, we finished two parts, two general parts. The first one was about search strategies. We covered search algorithms, we covered CSP, we covered local search, we covered also adversarial search. And then in the second part, we covered logical agents, where we assume that we have a knowledge base that is written in either probabilistic reasoning or either propositional logic or first order logic, and we saw how we can do inference in both cases, or at least some inference algorithms in both cases, like the resolution in propositional logic and generalized modus ponens in first order logic. Okay. Now we'll switch to the third part, which is about probabilistic reasoning. So what is probabilistic reasoning first? Probabilistic reasoning is a framework that allows us to deal with events that are uncertain. For example, if it's raining, how long will it take me to go to the university from my home? What is the chance that I will go there on time? If I'm suffering from high temperature and a headache, what is the chance that I will be tested positive for coronavirus, for example? What is the chance that this email is spam, given that I see a word buy in that email? What is the chance that if I take AI course in this semester, I will get an A? Okay, so all of these questions have uncertainty in them. Okay, we are not sure what will be the actual outcome. How can we deal in AI with these events? This is all about probabilistic reasoning. Whenever you see the word uncertainty in AI or in computer science in general, you directly think about probabilities. Okay. I know that, of course, you have some, knowledge about probabilities, but inshallah, today and the next lecture at least, we will go through all the stuff that we need to revise for this part, which is very important before we actually go into the main topic of this session. Probabilistic reasoning is used in many applications, as I said, in diagnosis. When you see some symptoms, what is the probability that the cause behind these symptoms is X? Also, another application here is speech recognition. What is the probability that, given that I heard this sound, then this is the actual word, or this is the next word, and so on. So there are many applications in computer science, and even in applications that we already see or we already use, that use probabilistic reasoning in one way or the other. Okay? Right. So as I said, today and inshallah next lecture, we will go through the revision for all of the things that we will need to know about probabilistic reasoning. So we'll go through very, inshallah, hopefully useful revision of these concepts. And what are random variables? What do you mean by joint and marginal distributions? What do you mean by conditional distribution? What are the rules like product rule, chain rule, and Bayes rule? What do you mean by inference, and what do you mean by independence? Okay, all of this will be needed, inshallah, for the next few weeks till the end of the semester. Okay, so that's the plan for today, and at least for the next lecture, inshallah. Before we start talking about the definitions and the revision, let me show you a motivating example here, game called Ghostbusters. So in this game, we have a grid, okay, and this grid has, of course, cells, and What is uncertain is that there is, what is certain is that there is one ghost somewhere, but what is uncertain is the location of that ghost. So in the beginning, we don't know anything about where the ghost is, but we are allowed to do one process called sensing. So we can sense in any of these cells. When we do sensing, or when we do reading in one of these cells, we get one of four colors: red, orange, yellow, or green. If we got red, then most likely that the ghost is under this cell. If we got orange, then most likely the ghost is one or two cells away. If we got yellow, it's most likely that the ghost is three or four cells away, and if we got green, then it is five or more cells away. You notice that I use the word most likely, and that's because we don't really know, okay? And because the values of the sensors are noisy, okay? There is uncertainty in the actual value, the actual reading that we get. So for example, if we are 3 cells away from the ghost, we might get red with 5% probability, and we might get orange with 15% probability, we might get yellow with 50% probability, and we might get green with 30% probability. Okay? So there is uncertainty and noise in the readings from the sensor. So red doesn't mean always that the ghost is here. There is a high chance that it is here, but it's not 100%. Okay? So that depends on how far we are from the ghost. Okay, so that's the game, and of course, eventually, after you do sensing, after you do some readings around, and whenever you have a good belief that the ghost is somewhere, then you can say bust, and then you can guess exactly where the ghost is. If the ghost is actually in the room or in the cell in which you pointed at, you win, otherwise you lose. So let me show you a quick demo for that. So here is the grid. So if, of course, initially you don't know anything, so you just randomly select one of the cells. Now you got green. Okay, green means that we most probably are far away. Okay, so next you probably will go somewhere else and click. You got red. Now, does that mean that the ghost is under this? Might be, okay, but we cannot be sure at that moment. We don't have enough evidence. We don't have enough observations. Okay, so the probability that the ghost is here is not very high for us to say bust. So we can decide to continue and do some readings around this cell. So we'll continue doing some readings here. Okay, so we do some readings around. We got green, we got orange. So that means that actually lowers our belief that the ghost is actually there, because if that's the case, then we would get so many oranges. Okay, but we tend to get more greens. Now we moved away, and we sense somewhere else. We started to get some yellows here. So let me repeat this part. So after we started to get greens here, we doesn't seem that the ghost is here. We got red here, green, yellow here. So that means that maybe the ghost is somewhere around. So we decided to continue with some readings here. We started to get orange here, orange again, orange again. So it seems like we are closer to the ghost. Okay, sorry. So it seems like we are closer to the ghost. So we'll continue sensing. Okay, so we got red here. Okay, we got red here. Red surrounded by oranges. So that means that the probability that the ghost is here seems like more than the probability that the ghost is here. Especially that we are almost surrounded with all oranges except this one green, which can happen, of course, with low probability. Okay, so our belief now that our belief that the ghost is here is higher than here. Okay, and probably if we model it right, then the probability here is really high, because there is a lot of evidence that says that the ghost most probably is here. Okay, so we decide at that moment that we will just bust. Comparing these two locations, we will bust, and we click here, we got a hit, which means that the ghost is actually here. So that's the game. Okay, that's the game. And as you see, as we collect more evidence, our probabilities will change, our beliefs will change. Okay, now in the rest of the lecture, inshallah, we'll see how we can model this problem. How can we measure the probability? How can we estimate the probabilities so that we can make informed decisions? Questions, Abdurrahman? Yes, but this one is green, which means that there is a higher chance that the ghost is here, because whenever you see green, there is high chance. It's not 100%, but there is a higher chance that the ghost is here. When you see green, when you see red, sorry, did I say green? No, sorry. When you see red, there is a higher chance that the ghost is here. But when you see green, when you get green, then the higher chance that it's not there. You are right that it might be here, not here, and you just got that because of the noise. It can happen. Okay, you are right. There is a probability that the ghost is here, by the way. Yani if we calculated the probability, and inshallah we know through the lectures how, if we calculated these probabilities given the evidence that we know, the probability that the ghost is here is not zero, will not be zero. But I'm quite sure that the probability that it is here is more than the probability that it is here. That's why probably we should bust here. Okay, did I answer your question, Abdurrahman? Okay, you're welcome. Okay, now to model uncertainty, we will use variables. Okay, you can think of variables as two types. Observed variables, which we call evidence. So these are the things that the agent really know about the state of the world. So for example, the readings that we saw. So we know that we got this red reading here, and green here, and orange here, and so on. We know that you have a high temperature. We know that the email has the word buy. Okay, so these are all evidence that we observed. We call these observed variables. Variables that we know the values of. We know their values. Okay? The other type is, of course, unobserved variables that we don't know their values. So we are not certain about. Okay? Like what is the cause of the disease? Whether this email is spam or not. Where is the ghost? So all of these are variables, but we don't know their values. So we are not certain about them. We call them unobserved. Okay, so the difference between observed and unobserved is clear. Observed, we saw it, we know it, we have the values for, we are certain about in the world. Unobserved, we are uncertain. We don't know their values. We might know something about their probabilities, Okay, but we don't know for sure their values. We didn't see them. We don't know them. Okay. Now, when we say a model means that we want to relate in a model, in a probabilistic model, we relate the variables that are observed with the values that are unobserved. We try to find, we try to reason over this by building relations between these variables, so that when we know some of these variables, we can infer something about the other one. When we know the observed values, we can infer something about the unobserved variables. Okay, that's what we mean by a model. So the model knows something about how the variables relate to each other. When we say we are building a model, we are actually building these relationships. These relationships will help us do the reasoning or the inference later. So in short, probabilistic reasoning gives us a framework for managing our beliefs and knowledge. Knowledge comes from the observed variables. Our beliefs come from the unobserved variables and come from inference over the observed variables to know something, to guess or to infer something about unobserved variables. Later, you'll see that unobserved variables will be divided into query variables, and hidden variables. We'll talk about that later, but for now, two types of variables. Some of them we know about, we know their values, we call them evidence or observed variables, and the other we don't, and they are called unobserved variables. Questions? I see Abdurrahman. Yes. Yes, of course. We have in the demo. Yes, we have unobserved variables, which are all the readings in all of these cells that we didn't read. These are unobserved variables. And also, the location of the ghost is unobserved, of course, because before we bust. We don't know where the ghost is, right? So this is unobserved variable. The observed variables here are the readings that we see. We know that we got a reading green here, we got an orange here, we got a yellow here, and so on. Okay, you're welcome. Any other questions? Okay, now let's define random variables. So a random variable is something in the world that we are uncertain of. Like what? Like whether it's raining or not, or it will be raining or not. Whether it's hot or cold. How long will it take to go to the work? Where is the ghost? What will be the sensed value in this location? Okay? What is the temperature? So we said what is the temperature? What are the words in the email or in the tweet or something? Okay, so all of these are random variables. So a random variable is about something in the real world. We are not 100% sure of their values. That's why they are called random. And of course, each random variable has a domain which defines the legal values for that variable. Okay? Usually in this course, we will denote random variables with capital letters. So whenever we use capital letters, we mean actually random variable. And as I said, each variable has a domain. So for example, R here has a domain that has two values, true or false. Very similar to the variables in CSP, if you remember. Okay, so the variable R here is binary and Boolean. It has two possible values, true or false. The variable T is binary but not Boolean. It has two values, hot and cold. It's not Boolean, it's not true or false, but it's hot and cold. The variable D here, which is distance, is real valued variable. So the domain is the real numbers. And L here is the possible location, so it's pairs of coordinates. That's the domain. In this course, we will always focus on discrete domains. As you see that sometimes the domains are continuous, sometimes are discrete. We will always work with discrete domains, although that the main concepts apply to continuous domains, but it will be much simpler to work with discrete for the course. Okay. Right. Now, what is a probability distribution? So in the probability distribution, we assign or associate a probability with every value of the variable. So for example, we said that temperature has two possible values, for this example, hot and cold. Okay, so in the probability distribution of that variable, we will have a specific probability for the value hot and another probability for the value cold. Okay, so for example here, we have 0.5 for hot and 0.5 for cold. Okay, so usually and always we will represent probabilities in a table like that. Okay, distribution, probability distribution in a table. Okay, and as you notice, T here is capital, okay, which means a random variable. And in a probability distribution, we list all possible values for that variable associated with their probabilities. For weather random variable, we have 4 possible values: sun, rain, fog, and meteor. And this last one is just very rare, so we put 0. Usually, whenever a value is very, very rare like that, we don't put it at all in the probability distribution, or we just assign very small value like 0.00001 to it. Okay. But the idea here is that we have all possible values for the weather, and for each one we have a probability. Okay, so here is 0.6 for sun, 0.1 for rain, and so on. So this is called probability distribution, and the distribution is a table, as you saw, of probability of values. Now, one thing that I forgot to mention here is that as a shorthand, whenever we have a binary variable like that, Boolean variable like R here, which has true or false, we use plus and then the lowercase version of the random variable to indicate true and minus to indicate false. Okay, so this is just a shorthand. So if the variable is R, we use plus R to indicate true instead of writing true, and minus R to indicate false instead of writing false. Okay. Now, we said that the distribution is a table, but the probability is a single number. Okay, so the distribution is a table, but probability is a single number. So if I want to indicate the probability that this variable has this value, we write it that way. Probability of the variable name equals the value, and that's now the value of the probability. And notice that we use small letters for the values and capital letters for the random variables. Okay. Of course, there are 2 rules for the probability distribution. All the probabilities have to be greater than or equal to 0, mostly positive, and the sum of the variables or the sum of the probabilities is of course 1. Okay. And the shorthand, we also use shorthand notation for this. Instead of saying T equal hot, we can just say hot, only in case that it is very clear what we mean, which variable we mean. Okay, so if all the domain entries are unique, if there is no 2 random variables that have the value hot, then we can, in shorthand, we can just say hot to indicate that we mean that this variable T is equal to hot, and so on. Okay, so that's just a shorthand notation. Now, what is a joint distribution? A joint distribution is a probability distribution, but over a set of random variables. So here we don't have just one, we have a set of random variables. So in probability distribution, we had a row for each value of the random variable. Here we will have a row for each assignment of values for the n random variables. We call that an outcome. Okay, so for example, here we will have a probability when each variable has a value. So x1 capital equals x1 small, x2 capital equals x2 small, and so on. So that will be a value here. Okay, let's say مثلا 0.3. Okay, of course we write it in short x1, x2, xn without the random, the names of the random variables. And that's how it looks like in a table. Okay, so that's a joint distribution because it has more than one variable. Each row here is an assignment of values to variables. And we have in the table all the possible combinations of values for all variables. So for example, for this row means that the probability that the temperature is hot and the weather is sun is 0.4. The probability that the temperature is cold and the weather is rain is 0.3. So that's called joint distribution because we have multiple random variables. It's not just one. One, it's just called probability distribution. But more than one, it is called joint distribution because we are jointly giving the probabilities. We give the probabilities when we have value for each variable. Okay? And of course must obey the rules of the probability distribution. So any probability is greater than or equal to 0 and the sum of all probabilities is 1. Now what is the size of that table? If we have n variables and each of them has d values, so let's say that here this has d possible values, this has d possible values, this has d possible values. What is the number of rows in that table, which is the size of the table? We have d for each, so it will be d times d times d and so on for all the variables, which means that we'll have d to the power n because we have n variables, which means that this is an exponential size. So as n increases, the number of entries, number of rows in this joint distribution table will increase exponentially. And whenever something increases exponentially, we should be worried about because it won't fit in memory at some point and it won't be efficient to handle. Okay, so at some point that will be very impractical unless we have very small number of variables. As we add more variables, this table will increase exponentially. So we'll have to find a way to break down this huge joint distribution table into smaller tables, and that's actually what we will study inshallah. But for now, joint distribution is full probability distribution with probability for every combination of values for the variables. Actually, we call every combination of values for the variables, we call them an outcome. Okay, so okay, so we call it an outcome. Every row here is called an outcome. We ran out of time. Do you have any questions? So this is just a quick small revision. We'll start with probabilistic reasoning. We discussed what is probabilistic reasoning, the example demo, and then we went through the definitions of random variables, probability distributions, and joint distributions. Inshallah, we'll continue next time. Any questions? Okay, so we'll stop here inshallah and we'll continue on Thursday. Assalamu alaikum wa rahmatullahi wa barakatuh.